Hello everyone. So today we're going to start on 12.3, the last section in chapter 12. So remember chapter 12 served as a introduction to linear system. So last section 12.2 we learned about elimination method, which allow us to solve a linear system. We will learn more different technique in solving more complicated system in chapter 13. So what we want to do in the last section of chapter 12, 12.3, is to talk about some applications. Remember, a lot of the time what we try to do is simply try to set up a system of differential equation to kind of model some real life situation. And then by solving those differential equations, it gives us a model that will allow us to actually describe something that actually happening. So what we're going to try to do in this section is to talk about some basic common application that we can use some simple linear differential equation, system of differential equation to do. So first one is actually what all of your favorite, fluid concentration. So what happened is when you dissolve some kind of chemical into a liquid, it would create a different concentration within the liquid. And if those liquid now flow into something else, then it would change the amount of chemical inside the container, the tank. So we have done this type of problem before, but now, of course, what we go do is talk about what happens if we have a system with multiple tanks connecting together. So here, this is example given on from your textbook on page 595. So what I'm basically going to try to do is try to go over this example with you so we can see how this works. So first, let me draw you a picture. So first of all, we have some kind of pipe going into a tank. This tank has an outlet that let out the excess water. And then you have two pipes that connected to a second tank, which also has an inlet pipe for more liquid to come in. So this is a two-tank system where we have a tank A and maybe a tank B, and both of them has a capacity of 50 gallons. And let's assume that they are full. Okay. And what happened is in tank A, there's a liquid going in from the outside, and this liquid has a flow rate which is 1 gallon per minute and has a concentration which is 1 pound per gallon. On this side, there's another liquid floating in, and this one has a flow rate of 1 gallon per minute also. But this is pure water. That means there's no concentration. The concentration, technically speaking, is 0. And then the liquid go inside, and then they kind of travel between the two tanks using these two pipes. So it really doesn't matter how this works, but I'm going to say like the first pipe, this top pipe, allow liquid to transfer from tank A to tank B at a rate of 2 gallons per minute. But notice that tank B now have 1 gallon going in from the top pipe and 2 gallons going in from tank A. Therefore, technically speaking, that total of 3 gallons per minute going into tank B. So those excess water have to leave. So it will go out this way on the bottom pipe at 3 gallons per minute. And so if you look at tank A, there's 1 gallon going in from the outside, 3 gallon coming in from tank B, but only 2 gallon going out to tank B, therefore leaving the excess liquid draining out on this side, which with a rate of 2 gallons per minute. So therefore, in this case, both of these tanks would maintain their volume of liquid inside. And as I say, both of them are right now filled with 50 gallons, with a 50-gallon capacity tank. So let's talk about this problem right here. So this picture shows two 50-gallon tank connected by float pipe with inlet and outlet, as shown. Okay. Now, can we have a tank where you have an out rate and in rate not matching so that the volume changing? Absolutely. But we go keep it simple and just do something like this where the volume inside the two tanks are actually maintained constant at full. And here let's define some of this stuff. So I'm going to go ahead and let's define x of t be the amount of solution or chemical. So here I'm going to just say salt, amount of salt measured by pound in tank A, and we're going to let y of t be the amount of salt, also pound, in tank B. Because of the liquid that floating into tank A that carry 1 pound per gallon of salt into tank A, we know that the amount of salt in tank A and tank B will be changing. With the amount of salt going in and going out, obviously that's what we try to figure out, is how this amount of salt inside changing. So that can be defined using what we call a differential equations. And then once we have the differential equation, which means now we can actually describe how the amount of salt inside each tank is changing, we can then try to find the function that can give us the amount of salt inside the tank at any given moment, which is what we try to find. Okay? So how do we do that? Well, so the basic premise is exactly the same. The amount of salt changing in each tank is based on how many pounds of salt going into the tank per minute, and how many pounds of salt out of the tank per minute. So let's try to figure this out. So let's start with talking about tank A first. So the amount of salt changing in tank A is given by the expression dx over dt, which is the derivative of the amount of salt inside. That's become the derivative and therefore become the rate. If you think about it, x is in pound, t is in minutes, so therefore we have a pound per minute expression here. So if I now look at this, I notice that first of all, we know that there is salt going into the tank, which is in 1 gallon per minute multiplied by 1 pound per gallon. So that's the liquid floating in from outside. Notice that I also have 2 pounds per gallon leaving tank A. So therefore that would be a negative rate. So therefore you have a 2 gallons per minute flowing out. But what would be the concentration? Notice that each of these expressions is basically a flow rate multiplied by concentration, and therefore give us a rate of change for the amount of salt. So I do need a concentration. The concentration in this case would actually be x pound, that's how much salt in tank, divided by 50 gallon. And that would be the pipe that go out from tank A to tank B. And now tank B also have liquid going into tank A, therefore increase the amount of salt inside tank A. So I'm going to add 3 gallon per minute, the flow rate, and then multiply by the concentration of the liquid in tank B, which is given to be Y pound per 50 gallon. And finally, the excess water drain out, and since drain out is leaving the system, so I'm going to subtract 2 gallon per minute. And I do need a little bit of room. Let's see if I can do that. Okay, that will probably do it. Multiply by the concentration of the liquid, which is X pound per 50 gallon. So what would this equation actually turn into? Well, it'll turn to this. dx over dt equal to 1 gallon per minute times 1 pound per gallon. Notice that the gallon cancel out, leave you 1 pound per minute. Minus 2 times x over 50. I'm dropping the unit because this, notice the unit will be the same. As a matter of fact, all of them have the same unit. Plus 3 times y over 50 minus 2 times x over 50. And remember this equation, the unit is basically pound per minute. Okay, and so this equation should turn to this equation, dx over dt equal to, if I'm looking at this correctly, is negative 4 over 50, or maybe I will write negative 2 over 25x plus 3 over 50y plus 1. So that gives us an equation that describes what happened to tank A. Similarly, you can write the same similar equation for tank B, which is dy over dt. So we look at it. First of all, I have 1 gallon of liquid coming in, but they're pure water, therefore have 0 amount of salt per gallon. And then it also have 2 gallons per minute of liquid going in from tank A, which have a concentration of x divided by 50. And then it leaving is 3 gallons per minute with a concentration of y over 50. So therefore, this come out to be dy over dt equal to 2 over 50, which is 1 over 25x minus 3 over 50y. And therefore, for my system of equation right there. Now, I know we're not using matrices to solve the system yet, but I do want to show you what this system look like. So in matrix form, because that's what we're going to do in chapter 13, in matrix form, this system of equation become this: d vector x over dt, which is technically dx over dt, dy over dt. And here x and y doesn't represent coordinates, but instead represent 2 different amount of salt in 2 different tanks. And that's equal to our coefficient matrix, which in this case are a constant coefficient matrix. Multiplied by the amount plus d vector b. So that would be how the system would look like if I were to write it in matrix form. And of course, right now it doesn't matter because we're not using the matrix form to solve the system anyway. So now let's try to solve this system. So I have these 2 equations, dx over dt equal to negative 2 over 25x plus 3 over 50y plus 1. And dy over dt is equal to 1 over 25x minus 3 over 50y. And so I can write this equation into x prime plus 2 over 25x minus 3 over 50y equal to 1. And the second equation can be written as negative 1 over 25x plus y prime plus 3 over 50y equal to 0. And now I'm going to go and write them into differential operator form. So therefore this will be d plus 2 over 25x minus 3 over 50y equal to 1. I purposely put the coefficient in front inside parentheses and change it into plus so that we have a negative coefficient just to make it look nicer. And the bottom one we have negative 1 over 25x plus d plus 3 over 50 of y equal to 0. So now my equation is in the right form for me to now do our elimination method. So I'm going to do that. So what I'm going to do is the following. So really up to me which one I want to eliminate. So I guess I just probably will get rid of the x. So I'm going to do is I'm going to multiply 1 over 25 to my first equation on top. So I multiply everything on the first equation by 1 over 25. And my second equation, I'm going to multiply that by d plus 25. D plus 2 over 25. Well, okay, maybe I should write this just to show you what is happening. Okay, so what happened to these two systems now that I'm going to do is I'm going to add them first. So therefore these two things would completely cancel out. So now I can actually deal with this part right here. So therefore what I have will be d plus 2 over 25 times d plus 3 over 50 y plus 1 over 25 times negative 3 over 50 y equal to 1 over 25. So now it's just a matter of me cleaning up this equation so we can solve for it. So if I'm looking at this correctly, that is d squared plus 7 over 50d plus 6 over 125, 1250 minus 3 over 1250 y equal to 1 over 25. So if I'm looking at this correctly, this come out to be something like this, which actually make it easier for me to actually kind of evaluate. That would be d squared plus 7 over 50d plus, this actually come out to be 3 over 1250, but I'm actually going to write it as 6 over 2500, which is 50 squared. Now, that is the reason why I choose to write it that way, because that actually makes it easier for me to factor. So if I'm looking at this correctly, I can see that I can actually factor this into d plus d plus 6 over 50 times d plus 1 over 50 of y equal to 1 over 25. So that's my equation in its most simplified form. Notice that this is a non-homogeneous differential equation because of the 1 over 25. So what I'm going to do is I'm going to first identify my homogeneous solution, y sub h, which will have to be c1 e to the negative 6 over 50t plus c2 e to the negative 1 over 50t. So now all I have to do is just try to figure out what would be my particular solution. And to do that, I'm going to use my undetermined coefficient method to do it, which I'm going to basically say if I take d of d plus 6 over 50 and d plus 1 over 50 of y, I should get 0. So therefore, this tells me that the solution to y should equal to this. Which we know these two are the homogeneous solution, plus a other solution C3. So that's actually make it very easy, because then this must be our y sub p. So if y sub p is equal to C3, then y sub p prime is equal to y sub p double prime, and they both equal to 0. So therefore, simply indicate that 6 over 50 square C3 should equal to 1 over 25. Because that will be what happened when I look at this equation right here. And d squared and 7 over 50d both become 0 when I plug in C3, and therefore just leave me with 6 over 50 squared times C3 equal to 1 over 25. And so that tell me that C3, if I do a simple cross multiply, or actually maybe I'll do this, I'll cancel that with the 50 square, and that become 2 times 50, where the 2 and the 3 cancel out. So it seems to me that C3 must equal to 50 over 3. And so now I have my answer for y. Y would be equal to, or maybe y of t is actually equal to c1 e to the negative 6 over 50t plus c2 e to negative 1 over 50t plus c3, which is a constant, 50 over 3. So that's one of my answers, which is good. So now I just have to figure out what would be the answer for x. So to do that, I'm going to pick an equation to plug in y. And of course, I'm looking for an equation where I don't have to solve for a differential equation of x. So therefore, that would mean the second equation right here would probably be what I want, which comes from this equation right here. So I'm going to just use that. So I know that dy over dt is equal to 1 over 25x minus 3 over 50y. So if I take the derivative of y, I would get negative 6 over 50 c1 e to negative 6 over 50t plus negative 1 over 50 c2 e to negative 1 over 50t plus constant derivative, which is 0, should equal to 1 over 25x minus 3 over 50 times y, which is c1 e to negative 6 over 50t plus c2 e to negative 1 over 50t plus 50 over 3. So, look like there's a lot of things going on, but I think we can handle this. I'm going to have the 1 over 25x stay right. Oh, actually, maybe I was put on the other side. Stay right where he is. And I'm going to try to move everything else to the other side. So, seem to me that this is negative 3 over 50 c1 e to negative 6 over 50t. So when I move it to the other side, become adding, so therefore become negative 3 over 50. C1 e to negative 6 over 50t. And that's also minus 3 over 50 C2, but when I move it to the other side, become plus 3 over 50, minus 1 over 50, become plus 2 over 50. C2 e to negative 1 over 10t, over 50t. And then 3 over 50 times 50 over 3 become 1, and this is negative. When I move to the side, become plus 1. So that's what 1 over 25x is. So if I multiply everything by 25, then that should work. So therefore, if I do that, if I multiply everything by 25, I would now find out that x of t would actually equal to negative 3 over 2, c1 e to negative 6 over 50t, plus 2 over 50 is actually 25. So when I multiply by 25, 1 over 25, so when I multiply 25, it cancel out. So it becomes c2 e to negative 1 over 50t plus 25. So that gives me the answer for x. So now I think we have our answer. So in this case, our solution, x of t, y of t, collectively would equal to, let me see. So I'm guessing we have c1 e to negative 6 over 50, or maybe I will write negative 3 over 25t, multiplied by negative 3 over 2, 1, plus c2 e to negative 1 over 50t, multiplied by, seems to me is 1, 1, plus the constant, which is 25 for x and 50 over 3 for y. All right, and so that is the answer that show the amount of salt in both tank A and tank B as a vector. All right, I think that's enough for this example, and we are 27 minutes or so, so I think we can stop here for today. And I have one more example I want to show you in tomorrow's video, and then that will be it. All right, I'll talk to you in the next video. Okay, bye bye.